It's a pleasure to see you all this evening. Thank you so much for joining this lecture. I hope to give you a bit of an overview of the Large Hadron Collider and a brief history of the LHC and the future of the LHC. But before we begin, in fact, Hannah has already done it for me. All good talks start with a safety briefing. So this is nonetheless one that we have to give. So yeah, there's going to be a few demonstrations and a few loud noises. We'll try and give some warning ahead of those loud noises, and you may wish to cover your ears, and there'll probably be a countdown for the larger ones. And of course, in case of fire, please do evacuate calmly. We have a fire exit here, which is being safely blocked by a hydrogen balloon, and one over there, which also leads out. And there won't be much opportunity for volunteering, but yeah, please do so if you would like to. Let me give you a brief overview of the talk. So I'm going to begin with a few perceptions of particle physicists. I'll talk us through the brief history of the Large Hadron Collider. So this is an inaugural talk, and it's a little bit about my own personal journey with the Large Hadron Collider. So that's been my career, and so I'm just kind of presenting how I've seen it and viewed it. So I'd like to talk about why I'm interested in working in that field, and then also to explain a bit how it works. So that's what some of these gizmos will hopefully demonstrate, what's been discovered so far, and also what are we working on here at Royal Holloway in the future, and future accelerators. So I often begin this talk as an outreach talk with a clip from the Big Bang Theory. I'm not going to do that tonight just in terms of time, but there's often many stereotypes portrayed in the media. But actually, particle physicists are pretty normal people, not entirely normal, but these are the actual physicists working at Royal Holloway or who have worked as students at Royal Holloway. So this is me. There's various graduate students behind me, people who have done or are doing their MSc or PhDs in accelerator physics, either currently. And so these are people, like many of the people I see in the audience, who are perhaps undergraduates or maybe thinking about becoming and joining a degree. These are people just like you who are just that one step on and are now doing their PhD in accelerator physics, working at CERN. And the one interloper, but who is very, very welcome, is Dr. Petri Heikkinen, who is over there and will be our pyrotechnic maniac and expert tonight. So thank you for joining us for this, and everyone else who's helped with the lecture so far. So to begin with, let's talk about the Large Hadron Collider, but in particular, why are we doing this? Why do particle physicists want to investigate the fundamental constituents of matter and its interactions? Well, it's all about what we're made of. It's all about the fundamental building blocks of matter. You know very well that matter is made of atoms. The atoms are typically made of a nucleus with electrons going around, and inside the nucleus we have protons and neutrons. And what we're interested in is what's inside that, what's inside a proton. And typically we know, I think, that inside a proton we have 3 quarks, and 2 up quarks and a down quark. And in fact, if you think about the so-called standard model of particle physics, the building blocks of matter are actually made up of just the following fundamental particles. So actually all matter that we typically see that's around us now, this table, you and I, are made of just up and down quarks that produce the protons, and also 2 down quarks and an up quark produce the neutrons, and these make up atoms and the electrons going around the outside. In addition, in a few radioactive events like beta decay, you also have something called a neutrino. But this family of particles isn't the end of the story, and this, as Anna mentioned in the beginning of the talk, is actually what got me interested in particle physics in the first place. When I went to CERN as a summer student, I discovered that there wasn't just one family of quarks, there were actually 3 families of quarks. There's heavier cousins, if you like, of the up and the down quarks, and also of the electrons. So we have the charm and the strange at the top and the bottom, or what we call the truth and beauty quarks, and also the muon and tau and their equivalent neutrinos. And in addition, there are the force carrier particles, the W and the Z bosons, which carry the electroweak force, and also photons that you're currently viewing me with, photons that carry the electromagnetic force, and also gluons, imaginatively titled, that stick everything together. But there was one missing piece in the standard model of particle physics, and that was the thing that produced mass for all the particles. And this was predicted by someone called Peter Higgs and a few others, and it's become known as the Higgs boson. It's the source of, in a sense, the field that gives mass to all of the other particles in our standard model of particle physics. And this had been predicted, but hadn't ever been observed experimentally. And so the Large Hadron Collider was proposed in order to hunt for the Higgs boson. And a part of my journey has been being on that journey of discovery and finding out about the Higgs and then learning more about it and wanting to progress knowledge further and further. Finding the Higgs isn't just the only question that we have. There are many fundamental questions that continue to challenge particle physicists. I've mentioned the first one: why do we observe 3 generations of quarks and leptons? There's no real reason that we know of why there are 3 at the moment. That's an interesting question. Are there particles or interactions beyond the standard model? Is there matter asymmetry in the universe? Or what is mass? This is related to the Higgs, and why is something called electroweak symmetry broken? And also we're interested in dark matter, or if you like, the matter that's invisible, that can't be seen in the universe, but we know exists from other ways that light moves around invisible objects in the universe. And so one way of investigating these questions is to use particle accelerators that enable us to reach very high energies. And why is that useful? Well, Einstein said that energy is equivalent to mass multiplied by a very big number, the speed of light squared. And so in order to generate a small particle, even though it's got a little bit of mass, you need lots of energy in order to generate mass from that energy in a particle collision. Another formula that's useful to think about is something called the de Broglie wavelength of a particle. Now, this is a slightly more interesting topic. You may have seen it before, but essentially every particle has a wavelength that is related to its momentum. And so if we can get particles up to a very high energy or a high momentum, we can actually probe very small length scales, very small wavelengths, if you like, of the thing that we're trying to explore. So with a typical with photons, we can get with a microscope down to viewing things at the level of the wavelength of light, or a bit lower, so sort of, well, a bit higher, about 50 microns you can easily resolve with a microscope. With an electron microscope, if you replace the photons with electrons, you can get smaller still at 2 nanometers or so. And then if you use a particle accelerator at really high energy, you can get much, much smaller still. So that's one application of particle accelerators. It's what really drove the development of accelerators, high energy physics, and understanding the world. But actually there are many applications of accelerators in the world that you perhaps may know or may not know. It's used in ion implantation in the chips in your mobile phone, in medical accelerators for curing cancer with targeted proton beam therapy, and all throughout industry. There are many other applications. And in fact, all the accelerators in the world, there are around 30,000 of them, only around 1% or less is used for high energy physics. But the Large Hadron Collider was proposed in order to discover the Higgs, and like all good resource managers in the debate in the House of Lords, Lord Elton said, "My lords, can my noble friend tell us what a Large Hadron Collider is and whether a smaller one might not do?" Always good to economize on things. But indeed, the Large Hadron Collider is a very large device. Why is it large? It's large because it reuses the accelerator tunnel that was there previously in the 80s and 90s, called the Large Electron-Positron Collider Tunnel, which fired electrons and positrons around, and that needed to be big because electrons and positrons suffer from a problem called synchrotron radiation, where if you have a really big radius, that problem is less of a problem. So that's why the LEP tunnel was so large, and using it again for the LHC, we therefore have a Large Hadron Collider. Now, when I was based at CERN as a summer student, LEP was still just running in 1999. That rather dates me, I'm afraid. But the exciting record that was broken at that point in time was the beams that were accelerated up to 100 giga electron volts. So an electron volt is the energy that an electron acquires if you accelerate it through 1 volt. But if you have 100 times 10 to the 9 of those, then that's the energy that the Large Collider got to. But actually, we needed slightly more energy than that in order to discover the Higgs. Going higher and higher in energy enables us to reach more discoveries and find out more things. So at this point, I want to invite us to think about the hadron part of the Large Hadron Collider. We're able to switch to hadrons, and a hadron is really a type of particle which, the simplest form of which is, say, a proton. And a proton can be easily found at the center of a hydrogen atom and a hydrogen molecule. And Petri here has a balloon that we earlier filled with hydrogen. And to show kind of the energy that's in that hydrogen molecule, we're going to split apart those hydrogen molecules and turn them into water by oxidizing the hydrogen. Now, at this point, I do want to mention that there will be a slight noise that's a little bit loud. And so if you would like to, I also don't want to, anyone has the opportunity to leave the lecture theatre if they don't want to be present for the large noises. That's also allowed. Or if you would like to be here, I would encourage you to maybe cover your ears, because there will be a pressure wave, and it will be quite loud. And there'll be a countdown so that we know when it's going to be. So we're going to, let's do it. Let's ignite the hydrogen balloon and observe the energy that's breaking. Why does Petri have one of those and I don't? I'm going to put mine on too. There we go. There we go. I've got one too. In fact, I'm going to stand back and let Petri do the lighting. So, are we ready? Perhaps we should have a countdown. Ready? Yeah. Okay, excellent. 3, 2, 1. Okay, awesome. Thank you, Petri. Well done. That's So, in fact, why did we explode the hydrogen balloon? It's because at the LHC, the protons started their life off as hydrogen, which is ionized and injected into the first linear accelerator of CERN that was called LINAC 2. It's now been replaced by a different accelerator called LINAC 4. LINAC 3 is for ions. But that's a picture of LINAC 2 at CERN. And actually, one slightly odd story, when I was a summer student at CERN, there was an interesting button that we saw when we went on a tour of LINAC 2. And it said, "Emergency stop." And I asked my tour guide, who was a senior chap at CERN, what happens if I push that button? Does it stop the Large Hadron Collider? And he said, yes, and also your career. So I thought that was exciting. So the question then becomes, how do we get those particles moving that we've just released from the hydrogen balloon? We use a property called, I've kind of said it, it's called, what's a good intrinsic property of a particle that we can use to keep it moving? Mass, momentum, all good physics words. Charge, excellent, yes, there are some physicists. Starting to worry, there's a few physicists out there. Excellent, so yes, we can use the particle's electric charge, and in fact we have a camera in front of us that shows a plasma ball and some of the electric charge that's there. But in particular, we can generate electric charge using a device called a Van de Graaff generator, and we have one of these in front of us here. So because of time, I'll perhaps do away with some of the volunteer demonstrations, but I just want to show you that we can move particles using a Van de Graaff generator. So let me, I've got some jammed heart tins here that we prepared earlier, and I'm going to pop this on the dome and see what happens when we turn on the Van de Graaff. Let's give it a go. It's coming. Ooh. So we're able to accelerate the particles from the top of the dome. We can also generate some nice sparks with the Van de Graaff. So if we bring a grounding sphere close to the top of the dome, which is at a high voltage, we can try and get the electrons to jump from one to the other. And if we do so, yeah, there's a bit of a spark there. It's not super big. But let me then connect the top of the dome to this device here, which is a cellar bowl, into which I have put some metallic strips. So let me actually switch to the camera so you can see what's going on. One sec. So hopefully you can see on the camera the inside of the cellar bowl. Is that live? Yes, excellent. So I have also a ping pong ball that I've coated in a slightly metallic paint so it's conductive. And if I pop the ping pong ball into the cellar bowl, not very much happens because it just sinks to the bottom of the cellar bowl. However, if I turn on the Van de Graaff and I charge up the strips which are around the cellar bowl and make the projector go a different colour, I can do the following. So this always excites both Pro-Vice Chancellors for research when you zap the projector in the room, and also teachers at school when you go and do a demonstration in their school. They love it when the projector goes zap. But it normally comes back again. Hasn't yet, but let's see. Okay, so hopefully that might be my camera actually rather than the projector. Let me just see that. Yes. There we go. Okay, it's not too bad. So indeed, we can actually accelerate the particle around the cellar bowl, and it's getting faster and faster. What we're doing is we're popping charge onto and off the ball with each time it crosses a strip. We put charge onto it, it then repels from the charge strip and is accelerated towards the next strip where it discharges, and then the process repeats over and over again, and we get up to a nice, relatively high speed with our ping pong ball. Zap one more time. Yes. Okay, it's okay, that's last zapping. So that's one way in which we can accelerate a charged particle. So, what we can do in reality is we can take a high voltage, and if we alternate that voltage between basically drift tubes, the particles can get faster and faster as they accelerate in the electric field between those two adjacent tubes. And using this method, you can get up to reasonably high voltages, sort of megavolts or higher, you can get the particles up to. And in fact, this is what was done. Very large Van de Graaffs were used in the early days in order to accelerate particles. But there's a better method, in a sense, that's used now at CERN for accelerating particles. And for this, I'm going to ask Dan perhaps to dish out a few paper cups or polystyrene cups and put them on the head. So I'm going to demonstrate something called a vortex cannon, which can propel particles. And to do that, I might just fill up my vortex cannon with some smoke. So one second. And so my aim is to knock the paper cups off your thing. So let me try this one. Okay. Oh, there we go. Oh, running out of smoke, but that's not too bad. That's these boys here are tough. Would you use gel and sort of injure? There we go. That's one. There we go. And one more. Oh my goodness. I'm not aiming that one very well. There we go. Oh, sorry. Almost. Yes. Oh. One more for that. Okay. Everyone? Yeah. Fantastic. So they're fun devices. You can make one at home. They're very simple. But what they're aiming to do is, I'm showing you that you can propel particles essentially from a box. And that's essentially what's done at CERN. But instead of having someone tapping the end of the box, we actually use an electromagnetic wave inside a box. And to demonstrate what happens, I'm going to switch again to the camera and show you this device, which is called a Kluntz tube. And the idea of this is that it's a resonator, a kind of box that traps a sound wave, and the sound wave generates nodes within the the pipe here using just a frequency generator. So if I turn on the frequency generator and turn it up a little bit, this is where it can get a little bit annoying. So if you don't like high-pitched sounds, you can also cover your ears at this point. But at low frequencies, not much happens. But if I turn up the frequency, you can see the particles are starting to move. And as I turn up again, I've hit various resonances of the device. So that's maybe one resonance. That's another resonance here. You can see the particles moving. There's another one somewhere there. Gosh, that's loud. Yeah. There we go. There was a children's TV program. What does that remind you of? The Clangers. There we go. That's the one. The Clangers. So, okay. What have we done? We've resonated some particles inside of our box. Why is that interesting? It's interesting because at CERN we have a similar kind of box, and this is it. It's called a radio frequency cavity. In fact, this is 8 cavities inside one metal tube, and it operates like this. When you have a particle moving along, and you time it such that it arrives at this point, it accelerates the particle through the cavity. What we're doing is we're pumping an electromagnetic wave into the cavity. The field is flipping back and forth, and if you catch that field at just the right time, it accelerates the particle through the cavity, and it gets faster. Brilliant. So we have a cavity. So a bit like a DC voltage that we've used with the Van de Graaff, the analogy is a skier skiing downhill starts at a very high voltage, but rapidly runs out of mountain. If you can continuously put in a wave, it's a bit like a surfer riding along on a wave. As long as the wave is there, you can keep accelerating that surfer. So one example of that is this little Lego accelerator over here. So if I take my particles, this is the radio frequency cavity. If I turn on the cavity, and I pop in the particles, I can accelerate them, and if I get it going fast enough, you can see that they should get up to speed around the accelerator, but they're all knocking into each other and not working perfectly. But an accelerator like this will continuously accelerate the particles, and much like the ping pong ball that was accelerated in the cellar bowl, these will get up to a higher and higher speed as time goes on. So if we're able to bring the particles round and reuse that same cavity over and over again, we can get up to a much higher speed. How do we actually bend charged particles in a loop? How do you deflect a charged particle? If you have a point charge that's moving, what do I need? What kind of field might I need to make that work? A magnet, yes, excellent. So a magnet, yes. So if I do this, does that ring a bell with anyone? Some people are knowing it's like the physics gang sign, right? So the physics gang sign of the left or the right-hand rule is how you can deflect a charged particle in a magnetic field. So at CERN, we use incredibly powerful, strong magnets that provide a vertical B field in order to provide a lateral force on the particles that are passing through the pipes. And so what you see inside these blue tubes at CERN are essentially 2 beam pipes for the protons going in opposite directions that deflect the charged particles in different ways, in different directions. And this design is based on a special property of certain materials called superconductivity. And superconductors operate at extremely low temperatures, or at least the ones that we found so far. And so I'd like us to just think briefly then about superconductors. So in order to bend a charged particle around in a loop, we need a superconductor. But what really is a superconductor? Well, I have some superconducting materials over here that I'd just like to show you very briefly. So if we pour some liquid nitrogen to cool down our superconductor. So I have a superconductor in here that's currently warm, but if I cool it down, it becomes quite rapidly superconducting. And what I can do, for example, is I can take that superconductor And one of the properties of superconductors is that they trap magnetic field lines. That's not quite cold enough. Let me just cool it down one more time. They trap electric field lines by something called, or magnetic field lines, by something called the Meissner effect. It's a essentially flux pinning of the magnetic field lines inside the Meissner effect. So if we take this out of here now and pop it above here, you can hopefully see that this is now levitating above the magnetic trap. So can you see that slightly levitating? You can kind of give it a bit of a poke, and it's still there. In fact, if we turn it upside down, it's fully stuck on to that magnetic field line. So we can bring it over here. It's completely levitating and stuck within the magnetic field. And so this is a very strong type of magnet. When it warms up, it rapidly becomes non-superconducting, and that's a problem because it's no longer a superconductor. And we'll see why that's a problem a bit more in a moment. But seeing as we like superconductors, let me just switch gloves because that one's become very crunchy. I'm going to cool it down one more time, and I've got here another type of track, which is a row of magnets which we've arranged so that it's like north-south, north-south, and that traps the field lines but in one direction, so it can still move along the track. So if we now take the superconductor out of here using the tongs, and we pop this over here, let's see if it can go on the thing. There we go. What we can perhaps do is we can take our favourite DeLorean and pop it on here, and what you can perhaps see is that the DeLorean is now floating above the track, levitating pretty well. It is actually levitating. I've not balanced it perfectly well. Perhaps I need to move it slightly. There we go. So there we go. So we have a levitating DeLorean above our track, which is quite an exciting thing. Where we're going, we generally don't need roads. So there we go. So that's our DeLorean. So why am I telling you all this? I'm telling you it because the LHC relies on superconductors and superconducting magnets in order to do its thing. And there's a lot of energy stored in the LHC beam. Each particle only has the energy, say, of a flying mosquito, but there are so many protons in the beam that the total stored energy of the beam is enormous. It's about the same energy of a very fast-moving train, or it can melt 1 ton of copper. But there's even more energy stored in the magnets. And so when the LHC first turned on, these magnets were connected together using essentially solder joints. And if those solder joints were imperfect, they have a small resistance. And if there's an imperfect solder joint, the temperature gets higher, the device becomes non-superconducting, and then it heats up even more. And so there was a bit of a problem at the start of the LHC in 2008. Just after 9 days of successful first operation, an electrical fault essentially caused the superconducting magnets to go non-superconducting, and the liquid that was used to cool them down, which in this case was liquid helium, evaporated very rapidly, and there was an explosion in the tunnel. No one was hurt, but the machine was damaged. Around 30 very long magnets were knocked off their concrete supports, and all this liquid helium was escaping, and there were lots of physicists running around Geneva saying, "Where's all the liquid helium gone?" And lots of things like that. So what we're going to do, just to demonstrate the expansion of a liquid to a gas very rapidly, is to make a cloud. And so again, I will ask Petru to come and help with this. So we're going to need, let's make a cloud. So we have 2 buckets of liquid nitrogen, and hopefully 2 kettles that have been pre-boiled with water. And what I would suggest we do, it's best to open the lid so they go in okay. Okay, that's good. Maybe I'll put one of those on too. And that's fine. Yeah. And I'm going to put one of these on. So, we're going to make we're going to rapidly expand the liquid nitrogen that's in the buckets into vapor. So let's see, is that okay? Yeah, let's go. Again, maybe a countdown. 3, 2, 1. Okay, that's kind of fun. So we've made a cloud. We've rapidly expanded that liquid nitrogen. Hopefully it's not too cool for the people in the front row. I did say it was a splash zone, so watch out. So let me, how long do we have before? We're okay for time. So moving on briefly, just to come back to what we have at CERN. CERN is that's the wrong clicker. Look at the other clicker. Can you see the other clicker? Lost it. I must have lost it in the cloud. Never mind. I'll just click here. So at CERN, we accelerate particles using the Large Hadron Collider, this 27-kilometer ring around which we fire protons at almost the speed of light. So they start off life, as we've just seen, or they used to, in a hydrogen bottle. They're ionized and injected into the first stage, which is a linear accelerator, and then go through a sequence of circular accelerators. It's a bit like the stages of the rocket, boosting the energy up to higher and higher energies with each revolution and in each stage of the rocket. So at the moment, they're in the superproton synchrotron, which accelerates them up to around 450 gigaelectron volts. Then they're injected into the Large Hadron Collider, which ultimately goes up to around 6-7 TeV. So we then accelerate particles and around in opposite directions and bring them into collision at 4 points in the ring. And when they collide, we instrument that collision point with large detectors that are like onions that have different jobs for each layer, and that's a whole other talk. In fact, there's an outreach, another inaugural lecture next term where more will be said about the Atlas detector. But that allows us to investigate what happened in the collision and understand what new particles were created and understand from the debris what kind of interactions have occurred. So the detector is shown here. This is the Atlas experiment that many of us work on here at Royal Holloway, including Veronique, who will speak later on. And it was very exciting to be there during construction and to see this kind of ship in a very large bottle being built. And I was a bit involved in the inner detector of the Atlas experiment. So this is actually sitting inside Atlas. Just behind us is the point at which the collisions will occur. And we built the semiconductor tracker, which is the innermost, one of the innermost layers of the silicon detector. It's a bit like a very large camera that you have on your phone, but the particles pass through it. So it was exciting to follow this detector out to CERN and to see it light up for the first time when particles flew through it. And so we're all kind of waiting in the control room. We're very excited to see beam splash as LHC delivered beam to our detector for the very first time. And this is an example of an event that we typically saw. So there's a short video about the, hang on. Is it going to come through? Probably not. Okay, the sound isn't working there, but essentially this is a video showing the discovery of the Higgs boson. So Rolf Hoyer was the Director General at CERN and was explaining that he thinks that we have it. We have found the Higgs boson. This is Peter Higgs himself, having just seen the announcement, and the two leaders of the experiments of CMS and Atlas, which jointly discovered the very significant discovery of the Higgs boson at that time. So this was an exciting moment for a physicist, right? So this is a bit like a rock concert for a physicist. There are actually people, including myself, lined up outside the lecture hall at 4 a.m. that morning in order to get into the auditorium in order to hear the announcement, because it was so exciting. Many Higgs events have been recorded. This is one example at the Atlas detector. So this is, the computer has nicely highlighted maybe 4 muons going through the muon chambers here. so a so-called golden event. But there are many other events that are collected and then analysed in order to get to this discovery point. So that was back in 2012 when there was a 5 sigma observation of the Higgs-like boson, and it was heralded as a giant leap for science at the time. And since then, we've been running the machine at higher and higher luminosities, so acquiring more data each year in order to really pin down our understanding of the Higgs boson, to really understand how it decays, what does it decay into, what branching channels and things does it have, and also are there other particles that we can look at and discover and understand. So it's all about a quest for deeper understanding of this new thing that has never before in human history been seen. And so that's what physicists have been doing over the past 10 years or so. In fact, it was very bizarre. I found it very bizarre when earlier this year, all of the LHC experiments at CERN were awarded what's called the Breakthrough Prize in Fundamental Physics. And there were lots of people who are famous celebrities in LA or wherever the award ceremony was, all applauding physicists for having investigated this. It was a very, very bizarre feature. But what really interests us is what comes next. So at the moment, we've just finished run 3 of the Large Hadron Collider, or we're about to finish it late next year. And then the CERN is going into what's called a long shutdown, a period where the accelerator is no longer running, but will be upgraded to provide more luminosity for the experiments. What that means is where the particles are colliding, we're going to tune the way that the particles collide so that there are more collisions per second, and we have more data to be able to analyze, because the processes that we're looking for are very, very rare indeed. Even though there are around 40 million collisions every second, a Higgs boson is only produced around once a day, I think, at the LHC or thereabouts. And so at the high luminosity LHC, that will go up by around a factor of 10. So this is the schedule for the upcoming shutdown. So we're currently somewhere here. Just going to show you. So we're currently here. Oh, there it is. Well done. Good spot. Thank you. So we're currently around here. So we've just got the last few bits of running, and then the red region is when the accelerator will shut down. And then by around 2029, after all the injectors and the LHC has switched on again, perhaps by around quarter to 2030, we'll switch on again for run 4 of the LHC, and then there'll perhaps be another shorter shutdown to upgrade the accelerator again. So Ronald Holloway is very much involved in developing this future for CERN in what's called the High Luminosity UK project. It's essentially increasing the number of collisions from something like this, maybe 23, or it was nominally 23. I think we're now at around 60 every bunch crossing, up to many, many more in future inside Atlas. And we're also involved in the instrumentation that's being developed for tuning the way the particles are colliding. So that's, again, another talk, but here we are installing devices which were built in our labs here over in the physics department just